Well, Heidi ho. We recently saw the direct substitution property, which says that if we are looking at a polynomial or a rational function, and we're looking at the limit of that function as x approaches some value in its domain, then we can directly substitute that value in to figure out what the limit is. And unfortunately, that doesn't work when we're finding the limit of a function with a number that's not in its domain. So we need some other tools. And I want to look at an example today of a function that can be simplified and how we can use that to our advantage. And the example we'll use is the limit as x approaches 1 of x squared minus 1 all over x minus 1. Now, this is a rational function, so you might think that we can use the direct substitution property. However, when we plug in x equals 1 to this function, when we plug it in the denominator, we end up with 1 minus 1, which is 0. So that's not a part of the domain. So we certainly can't just substitute that in. However, if we look at this function, f of x, I'm going to name it f of x just in case we want to refer to it later, which is x squared minus 1 over x minus 1. You might notice that the numerator is a difference of squares, so we could factor that into x plus 1 times x minus 1, and all of that is over x minus 1. And you're probably noticing that there's a common factor in the numerator and denominator. We've got an x minus 1 in the numerator and also in the denominator. And your intuition might tell you to cancel those, but we need to think about whether or not we are allowed to cancel those. And you probably have never put that much thought into canceling a common factor in the numerator and the denominator. But here's the thing. When we're canceling a common factor in the numerator and denominator, that's really a shortcut for dividing the numerator and denominator by those factors. That's actually what's going on behind the scenes. So if we wanted to cancel those out, what we would be doing is dividing the top and bottom by x minus 1. And we need to ask ourselves if we're allowed to do that. And there's an interesting thing here. In this problem, we're looking at the limit as x approaches 1. So remember, when we're looking at a limit, we want to know the x values near 1 in this case, but we don't care what happens at 1, right? Remember, when we're looking at a limit, we want to know what's happening nearby a certain place, but the actual value of the function at that number, in this case x equals 1, doesn't matter. And so in the context of looking at the limit as x approaches 1, we are considering x values that are near 1 but not equal to 1, specifically not equal to 1. And if we look at these factors of x minus 1, if we want to divide by them, the only case we would have a problem is if x equals 1. Because when x equals 1, we would be dividing by 1 minus 1, or 0. But specifically, that's the one value we really don't care about. We care about the values nearby it, but specifically, we're not looking at the values where x is equal to 1. And so in that case, we can divide the top and bottom by x minus 1, and that leaves us with x plus 1. And I want to talk about the original function and then this new function. Let's actually call this new function g of x, because there is a difference between this original function and this quote-unquote simplified function. These functions are equal to each other for every value of x except x equals 1. Because when x equals 1, g of x is defined, but when x equals 1, f of x is undefined because we've got a 0 in the denominator. When we take a function and cancel a factor in the numerator and denominator, we end up with a new function that is equal to the old function everywhere except there might be a small difference in domain. That division that we did gives us a difference specifically when that factor was 0 or when x equals 1. If you were to draw the graphs of these two functions, the difference you would have is that f of x is undefined at 1 and g of x is defined. So this graph, if we were to graph it, I mean, you know x plus 1 is a linear function. That's going to be the graph of g of x. And then f of x is equal to it everywhere except one point, one value. And so at x equals 1, we actually would have an open circle. This would be the graph of f of x. So these two functions are identical for everywhere except a single point where g of x is defined but f of x is not defined. And that's what happens when we cancel factors in the numerator and denominator. When we simplify functions, you're not really looking on such a granular level when you first learn this, several semesters ago in an algebra class. But the new function is not technically the same as the old one. There's going to be a small difference in the domain generally. And so these functions are a little bit different, but for the purpose of the limit, we end up getting the same value. Because remember, we don't care the value of the function at that one point. We just care what's happening nearby. And nearby, these two functions are identical. So we can say that the original limit is the same as the limit of the factored version. And then we can cancel out those factors and say that that limit is equal to the limit as x approaches 1 of the simplified function x plus 1. And now this is a linear function, which falls under the category of polynomial functions. And so we can use the direct substitution property here. So substituting in 1, we get 1 plus 1, or 2. So in this case, the limit is 2. And we have a rule that covers this situation and some similar situations. Let's take a quick look at that rule. The rule says that if f of x is equal to g of x, so long as x is not equal to a, so these are two functions that are equal everywhere except for the value a, then the limit as x approaches a of f of x is equal to the limit as x approaches a of g of x, provided the limit exists. And that's what's happening here. We have our original function, x squared minus 1 over x minus 1, and that's equal to our simplified version, our simplified function, x plus 1, everywhere except at that single value, x equals 1, because that value is not in the domain for one function, and it is in the domain for the other function. And so because these functions are equal everywhere except that value, that means that the limits are equal. And so we can, to find the original limit, instead find the limit of the simplified version. And in fact, it's fine if there are a couple of other points where these functions are not equal to each other. You might have multiple common factors that you end up canceling. And if that's the case, for example, you might have an original function where there's a few values that aren't in the domain, and then a simplified version where all of those values are in the domain, because every time we cancel out a common factor, we might change the domain of the function by a single point. And it's okay if there are a couple of extra places where that function is undefined, because remember, when we're looking at the limit, we're looking near a certain number. And if we're looking near this number, for example, it doesn't matter if there are other points kind of a distance away. When we're looking at the limit, we can zoom in far enough that those points are outside of where we're looking. So it ends up not being a problem, even if there's a finite number of points where those functions are not equal to each other.